today, if you look at the title, we will have a very up-to-date, very, let's say, fashionable topic. And this is the application of machine learning stuff to stock market. So we have Dr. Buhong Liu, actually, who joined our department recently, actually, from last year, I think, and then formally beginning of this year. So Buhong is a lecturer in finance at School of Finance and Management. And he got his degree. As you can see, it's very hard. He got his degree in computer science from King's College London. And he got his Bachelor of Science from Wuhan University, also in the similar direction, applied mathematics and financial mathematics. And I think he specialized in I see that he specialized in the application of financial, artificial intelligence in finance and economics. And this paper is basically directly in the stock market. So he has done some other different modules or programs from London School of Economics and also Imperial College London. And before he came to SOAS, Buhong was a lecturer in financial economics at the Adam Smith Business School, University of Glasgow. And I see here he has also some industry experience, which we never talked about. So maybe I'm curious to know what kind of industry experience. And he worked as a data scientist and quantitative research, as you can imagine. So I think that's his direction. He's basically a scientist. He's a scientist in data science, and he now applies those newly developed technology to our traditional finance. Let's say what happens, and this is just one of the examples for this type of application. So Buhong, when you are ready, please. As I said that, our audience probably need a little bit more explanation of the terminologies, etc. Thank you, Buhong. The floor is yours.
Okay, thank you for the introduction from Professor Hongbo. And as you can see, so my background is in computer science. So, and actually this paper, my co-authors, they are all from the same department when I obtained my PhD degree. So this paper is written, in a computer science or artificial intelligence format or text. But we aim to submit this paper to we have already submitted to a traditional finance journal, but we also, expect to have more comments, feedback from, the finance community so that we can extend our work. So the topic, the decomposition of microstructure, dynamics in named outbook. So, in the context of this paper, the so-called microstructure is quite simple. So you can take it as a very classic classification problem. So I will explain this topic, this problem later. So let's start from the introduction and motivation. So as you can imagine right now, we have experienced the development of the so-called the high frequency trading. So we have to deal with so many data every day, every hour, every minute, and every second. So it will cause one problem. So if we are going to construct, for example, the prediction of the moment of the named outbook, Okay, or let's make it more specific, the best ask price or the best bid price. Okay. It will cause a problem because if we try to apply the traditional statistical approach, let's say some most classical one, ARIMA or GARCH, okay, it will cause a problem that so we have to deal with too much data. The size of the data set will be, too large, and actually we cannot really deal with this data in a very efficient way. But the good news is that so the development of deep learning, so this computational approach has provided some sufficient way to deal with the large volume data. And one problem, as you can imagine, so if you remember, maybe 10 years ago, a software which is called the AlphaGo was established, at the UCL, and that is the first time so we can beat the professional Go player. So we find if we perform the deep learning, actually the AlphaGo, is involved with the reinforcement learning. So one specific machine learning model in the deep learning area. So if we feed sufficient data, so this model can generate very good results. And that is the one basic motivation of this work. So since the statistical model may fail in the in the context of the high frequency trading, so why we do not try the deep learning model? So that is the basic motivation. And our research question or our aim is to understand and model the linked output dynamics from a time series decomposition perspective. So that is it involves the second question. So if we take the dynamics of for example, the best ask or the best bid. Okay, so there are two time series, but time series forecasting is a extremely difficult question. So we need to find some way to make it be easier to do the prediction. So we think about
Buhong, can I interrupt? Can you please explain limited order books?
Okay. Yes. Sorry.
So what does this terminology mean?
Okay. Yeah. So, well, I'm not sure if you have any experience of do the stock trading, equity trading. Okay. So when you do the trading in the exchange or in the electronic platform like trading on 212. Okay. You have to choose you are going to buy a stock or to sell a stock. Okay. And if you are going to buy a stock, let's say a stock of Apple, okay, you need to set a price, let's say 100 pounds. So this is typically a limit price because it means you are going to buy one share of Apple stock with a maximum price 100 pounds. So that is a limit order. And similarly, if you are going to sell one Apple stock, so you will choose a limited price, let's say 120. So it means the minimum acceptable price for your sale. So when everyone submits the limit ask order or the limit bid order, so we have for example, the exchange will establish a pool for this specific stock, and all these outstanding limit orders will be collected in this pool. And when this pool observe a new limit order, arrival of a new limit order, it will match the existing or the outstanding limit orders in the pool to see if we can have a match. Okay, so let's say in this pool the minimum, the sale price is let's say 110, and it observed a new limit buy order with the price 120 arrives. So one transaction will match because the minimum acceptable price is lower than the maximum acceptable buy price, and otherwise no transaction will happen. So we will have we'll have
very clear.
Yeah.
Thank you. So I think we know everybody understands what you are talking about now. So yes, Continue, please. Yeah.
Yeah. So every second you will see the dynamics of in the book or the pool. So we say every second, every tick, you will have a best, the highest bid price or the lowest ask price. So we have two time series. Right. So that is the our target. And our contribution is to propose a deep learning model to forecast the moment of this time series. So to simplify this question, so in this paper, we are going to do a classification forecasting. So it means, so given the current information, we will forecast if the price will go up or maintain the same level, or it will go down. So it is a three category classification problem. So that is the so-called microstructure forecasting in the context of this paper. So we're going to introduce the dataset we are going to use in this work, in this research. So first, we are going to verify the effectiveness of this application, and to distinguish if one specific deep learning model will outperform the other one and under what condition. So to verify this hypothesis, we introduce the synthetic dataset first. So here you can see we have three synthetic in the output dataset, and actually, so they are composed in these three different components, basic components. The first component is a trend time series. So it is simulated with the preset, the trend function. And the second component is a seasonality time series. And the third one is a noise time series. So every synthetic named output is the combination of all these three basic components. Okay, but the difference is that, okay, so for the first synthetic named output data, so we have only one trend component and a noise component, which means we do not introduce the seasonality component in the first synthetic data. While for the second one, the synthetic named output data 2, we have all these three components. And for the third synthetic named output data, so we have all these three components: trend, seasonality, and noise. But the difference between the third one and the second one is that, so the seasonality level will be more stronger in the third synthetic data compared with the second one. So that when we compare the performance of our proposed model in these three synthetic named output data, we can see, so what is the which method will have a better result under which condition. So that is the first step of our work.
Yeah, and Buhong, can you explain a little bit about how did you generate or create the so-called synthetic data?
Okay, so we just use three preset functions. So one is, so the first one is a stochastical process function generator. So it will generate. So I'm not sure if you have any background about like the Gaussian process, something like that.
I heard that. I know something, but not everybody knows. So it is a stochastic process. So you are trying to model volatility, and that's so I understand this synthetic data was generated by languages, deep learning languages, right? Or programs.
Yeah, it's generated by a program. So we write a code to simulate a Gaussian process with a non-zero trend or non-zero coefficient, so that it will show. You can see take it as an example. So you will see upwarding trend. From from the beginning to the end of this period. So we just use this stochastical process to simulate a trend process, a trend time series. And similarly, we use another function to generate a time series with strong and weak seasonality. And the last one is a white noise process. So to generate some noise with zero mean. And we put all these three components together, and it will look like
that's clear. And in terms of the functions, that you have to assume which kind of distribution that stock market follows. So you do have the justifications for why do you use Gaussian, why do you use white noise process. So why did you choose those four?
Okay. Yeah. So maybe we didn't write about this part in our manuscript, but our motivation is that so from the previous research, so we have made some literature review, and most literature review, especially using the traditional statistic model. Okay, so they also try to use the decomposition method to abstract some basic components from a time series of the linked notebook. And these three, so trend one, seasonality one, and the random one, so these three are most common, applied decomposition results from the previous research. So that is the main reason we use these three components. And in this, and we do not use a very specific the process generator to make it the combined process to be matched to the real stock time series. It's just because first at this step we only need to verify if we propose different models, so will they be successful in different contexts. And the second reason is that so we have the historical stock data. So we will apply our proposed model in the real, the stock data. So that's why we do not model, the historical, the stock data here.
Yeah. Okay. Thank you. Continue, please. Yeah.
So that. And this figure, so you can see here is a specific mid price. So we generate the ask and bid, and the so-called mid price is just the average of the best bid and the best ask. So to simplify, because we only need to show one time series, it will more clear here. So that is synthetic data we used. And the second experiment, so we used the real crypto linked notebook data. And so crypto currencies, I assume, so you may hold some of them, like Bitcoin, so the most popular one, right? And like ETH or some other cryptocurrencies. So the unique feature of the cryptocurrency market, the compared with the traditional equity market is that so this market will run 24/7. So there is no so-called trading date in the crypto. So every time, every second, they are traded. So that is the uniqueness of the cryptocurrency. And another uniqueness is that so because there is no real central governance of the cryptocurrency market. So let's say, for example, in LSE, London Stock Exchange. So if the moment of one stock, have a very sharp moment. So maybe the investigators will do some the regulator will do some investigation. Maybe the stock will be paused to be traded. But in the cryptocurrencies, there is no such authority to do that. So the moment of the cryptocurrency is tend to be more sharp than the traditional equity market. So it's very easy. It's very common to say, for example, 30%, 40% movement every day. So that is another uniqueness of the the cryptocurrency markets. So that's why we introduced the cryptocurrency dataset in our experiment. We are going to see if our model will have a consistent performance in different markets.
But Buhong, in my understanding, the direction of a crypto market should not be the same as the stock market. Are they the same?
So what do you mean the direction?
The price, the movement of the price, let's say.
They apply the same trading mechanism. The auction mechanism. So they also use the limit output mechanism to do the trading.
Oh, okay.
Yeah. So
I'm thinking about maybe, if the stock market is not doing well, maybe the crypto market is doing well because, people get the money out from one market and then they find some other market to invest. So, but this probably does not matter. You according to you, right?
We consider these things. So but because we just miss, we cannot make a sufficient experiment to do that. So we try to explain. We try to avoid the how to say that, the difference coming from the different date by investigating the market in sorry, here's some background noise. In different days, yeah. So here, for example, we have BTC to US dollars. So on 8 September 2024. And we also consider the BTC to USD on the later 2 days. Maybe, they are in, all these 3 days are together. So maybe you may argue. So these days are more concentrated, and we may not observe too many differences. But but that's our first verification, because we have to pay for this data set, and we can not only afford this right now. But we are going to extend this work to see if, for example, if our model will work, for example, in 2024 and also in 2016, if we set up a large time gap. Okay. So in addition to the same cryptocurrency on different dates, we also consider the different cryptocurrencies like ETH, SOL, PEP. So they are different cryptocurrencies on the same day, so that we can see if our model will work across the different cryptocurrencies and across different time. Okay, so here is the basic descriptive statistics about the cryptocurrency we are going to use. So because we consider 24-hour continuous 24 hours, so the time steps we can observe is very large. So it's around 800,000. Okay, so it's an ultra high frequency data set. Okay, and the final one, the limit output of the stock market. So we use the FI 2010. So this data set as the data resources in this study. So it's a Finland. It's the limit output data set is from Finland, and we consider the following selected companies. We randomly select these target companies, and we also collect the 10 continuous days from 1st June 2010 to 14th June 2010. So you can see here, because of the restriction of the trading time of the stock market, so we have quite few time steps here compared with cryptocurrency. So you can see here, 14 days, right? I believe there are 10 trading days, and we have around 70,000 time steps. But for the cryptocurrency, so for only 24 continuous hours, we can have like 800,000 time steps. So you can see, so that's a quite different, unique feature of the cryptocurrency market.
Buhong, can I ask you, why do you use this Finland dataset? So is there any particular reason, or what are the other available data sources for this type of research?
Yeah, so the reason is that, so first, the availability. So we can have this data set for free. And also, we observed some previous research using this data set, and so we would like to make the fair comparison in our future work. So that is the main reason. These two reasons. This is the basic descriptive statistics of the selected companies. And let's move to the methodology and models. So for the synthetic linked output data, so we generate 10 levels of odd price for ask side and bid side. So as I explained, so when we consider the bid side and ask side, so we consider the best bid and the best ask, so that we can have the mid price. But actually in the linked output, so we have many years on both sides because too many traders will submit their linked orders. So the lowest ask price we can call it the level 1 data. And the second lowest ask price, we call it the level 2 data. So you can see we can have 10 levels on both ask side and the bid side. And for the cryptocurrency linked output data set, because we collected this data from the BS, a very famous cryptocurrency exchange, and their API provides 1,000 levels of the order. So you can see it's very complicated. So to keep the computation of the experiment to be within the reasonable period, so we select 20 levels of the cryptocurrency linked output data from the 1,000 levels provided by the exchange. And for the stock linked output data, so the original data source provide 10 levels, and we use all 10 levels. So that is the data set we use for our experiments. And the next part is about how to do the classification and how to do the machine learning training and testing. So as I explained, so we consider it, we take it as a time series, but actually it's a high dimension time series, because for each node of the time series, for each component of the time series, so everyone will have two dimensions here. So if the price is, sorry, 4 dimensions here, because there's some mistake here. So here we should have, like, for the synthetic data, right? So we should have, there is typo here. So we should have 20 dimensions for each component of the time series, because we have ask 1, bid 1, ask 2, bid 2, ask 3, bid 3. And also the volume of ask 1, volume for ask 2, volume for ask 3, and similarly, volume for bid 1, volume for bid 2. So if we consider 10 levels on both sides, so we should have 20 numbers describing the price and another 20 numbers describing the volume. So we should have 40 dimensions for each component in this time series. Okay, and similarly for the crypto one, so we should have 80 dimensions for each one. And for the stock linked output dataset, we have 40 dimensions for each component of the complicated time series. So that is a complete dataset we are going to feed to our machine learning models. And the target, because we only consider the moment of the mid price, so the formula to compute the mid price is given here. So we only consider the average of the best ask and the best bid, and we consider the change between the current mid price and the next current price. So we make it we make the classification problem into three different categories. So one is upward, another one is stable, and another one, and the final one is downward. So we give us threshold P to describe. So on the so if the moment is within the threshold P, so we take it as stable, and if the moment is higher than threshold P, we take it as upward, and similarly classified as the downward. So that is the pre-process for the dataset. And in this experiment,
Buhong, can I understand a little bit more? Yeah. So those definitions, you as a researcher, the group, you actually decide that you define in that way, and then this is written in the program, and then you apply the program, and you use the machine learning things to generate the data based on the available other information, right?
Yes.
Okay. Yeah. So those are the things that as a researcher you decide, and then you input that into the program, and then you let the machine learning running, and then you generate the data, right?
Yes. So the result is generated by the program. So we have no, in addition to the preset of the how to generate this time series. So we have no interaction with that. So it's completely generated by the program.
Yeah, of course. Yeah. But Buhong, I know little about those machine learning things. I do not know the programming, but I understand that when you do this, we do not need to have any predetermined assumption on the distribution, i.e., there's no distribution whatsoever. Is that true? But I thought you have a lot of assumptions. You restrict the data, the phenomenon should follow a certain, stochastic distribution or movement, and then you define them, and then basically, as a human being, you actually defined a lot of things.
Yes. So for the synthetic data part, that's true, but just as I explained, so for the first part, we only need to show. So if we have, for example, if we have a strong seasonality, if we observe a time series performs a strong seasonality, so maybe our proposed model will outperform the traditional LSTM. I will explain later, something like that. So we are going to verify these guys. And for the second one and third one, I mean the cryptocurrency and the historical stock data, we have no assumption. We have no determination about this. We just apply our model into that. Yeah. And another benefit, I believe, of performing machine learning model than performing the econometrics model is that we do not need any assumption about the properties of the time series. So we do not need to be stationary, to be linear, something like that. So that is one benefit of performing machine learning models. And so I will show you the models here. So the model we are going to use as a benchmark is called the LSTM. So actually, it's very classic, or you can say it's an old model because it was proposed around 30 years ago. Okay, so we just use it as a benchmark. So the LSTM model. So from the name, you can see the LSTM. So it has it combines both the long-term dependency and short-term dependency into one model. Okay, so well, I'm not sure if I have any time to go through the details of that, but the uniques of the LSTM compared with the let's say the ARIMA or GACH is that so for ARIMA and GACH we have to preset the P and Q. So the terms has been presetted has been preset. But for the LSTM, okay, so we can feed it as long enough terms into the model, and it will select. So the most efficient long-term dependency and the most efficient short-term dependency. So that is one benefit of that. We don't need to do any, the manually preset of the model. So that is a benchmark model. And another one, the time to vector representation. So LSTM can, to some extent, to describe the different and the long-term and short-term dependency, but it cannot capture the seasonality very well. So that is the drawback of the LSTM. So the time to vector representation is a good addition to that. So you can take it as the so how to explain that? So when we feed this data into the machine learning models, these models cannot recognize the meaning of the time. So they don't know what is the meaning of, for example, the Q1 2020 and the Q1 2021. So they have some similar. They might perform some similarity, right, because of the seasonality. But the machine learning models cannot recognize that. Mm-hmm. So the time to vector representation is just to embedding the time steps into some unique numbers, and these numbers will contribute to some fixed effects to the model. So let's use a simple example to say that. So if we put, for example, the Q1 2020, and we embedding into some numbers like 2020 01, and we can embed the Q1 of 2021 like 2021 01. So we have two numbers rather than two time steps. And in the computation of the machine learning models, they will find, okay, if we find for example, the dataset performs a strong seasonality. Okay, so it will do some modification to the embedded numbers 2020 01 and 2021 01. So we just take the last two digits of this number as the feature to make the prediction, so that they will show some same features because of the seasonality. Yeah, I'm not sure if this example is clear to explain why this model can have a good performance in the recognition of the seasonality. Yeah, but anyway, so time to vector representation is a good addition to the LSTM. So LSTM recognizes the long and short-term dependency, while the time to vector can recognize the seasonality. And the final model we are going to consider in this work is called the attention. Okay. So attention, well, it's a very fancy machine learning model recently. I believe all of you have heard about the ChatGPT, right? The successful application of ChatGPT. The underlying algorithm is called transformer. Yeah, but we will not use transformer here. The transformer is modified based on the attention. Okay. So the uniques of the attention or transformer is that it will adjust automatically the weights of different, the weights of different, the figures or the numbers in previous times. So let's say, if we are going to do, for example, the GDP forecasting, okay, and we find the GDP of 2009 is highly affected by the the financial crisis in 2008. So if we use attention to make the forecasting of the GDP of 2009, it will increase the weight of GDP of 2008 and reduce the weight of GDP of 2007. So it will do the automatic adjusting of the weights. So it's no equal weights or fixed weights of the previous previous data. And when it comes to the forecasting of, let's say, GDP of 2020, so the effect of the financial crisis in 2008 has decreased a lot. So it will reduce the weight of GDP of 2008, and rather than it will increase if it finds, for example, the 2020 is highly relevant to, let's say, 2018. We assume that, so it will increase the weight of 2018. So anyway, so attention is just to automatically adjust the weights of previous data set. So that is on my principle of that.
And Buhong, can I ask you a question, just for the sake that everybody follows? And so you now, for the past 3 transparencies, you presented the 3 models. And first of all, are those the established model, or any of them is your model?
So all these 3 are established models.
Okay, so all those 3 models are already there and in the literature, but you want to use them, right?
Yes.
Okay.
Yeah, because in the before, so attention model is most adopted in the NLP problem, so natural language problem. So it's like we have some word, let's say, how to say, the classification problem. So when it observed, so we have a word classification. So there is high probability, the problem will come after that. So we can take the word as some sequences similar to the time series. Also, there is no the time dependency there, but there's some like rationale or logic relationship like that. So we just transfer the application of the attention or the transform model from the NLP context to the time series context. So that is
I see.
Our proposed work. So here is the model architecture here. So we put the price and volume to LSTM and to see if we can have good classification. And then we put the time to vector and as an additional feature to recognize the seasonality in addition to LSTM. So that is our second proposed model. And now, actually, I missed the last one. So the last one is the model using the attention mechanism, so that we take it as a benchmark model, and we compare this one LSTM plus time to vector, and the third one time to vector and attention. So that is what we are going to compare in the experiments later. So when it comes to the experiment, so here is a list of experiment setup. So all models are implemented in Python using some external libraries, and there are some established libraries, and we can use that with some required modification by ourselves. And all the training, the calculation are performed on King's computational research platform. So that is a high performance computing environment, so we can use. And actually, it will take around like 1 week to train and test each model. So that is the time consumption. Okay. And here is some more specific technical setup. So maybe I can just skip that. And We also use the cross validation. So it's also a standard procedure in AI community to do such time series forecasting. So you can take it as so suppose we have a whole time interval and we split into k folders. So we can index it from 1, 2, 3 till k. Okay. And what we do is just we use the folder 1 to make the first forecasting, and then we move to the folder 2 and use the folder 2 to make the next forecasting. And we will have some overlaps, and we use average of these overlaps as the final forecast results. So that is the so-called the cross validation process. And next is the evaluation metrics. Well, I should write. So what does these terms mean? So TP means the true product. So it's like let's see how to explain that. So it's like suppose we have two categories. One is positive and the other one is negative. Okay, so the TP true positive, it means our prediction result is positive and the real result is also positive. So we make a true positive forecasting for that one. Okay. So FP false positive. So it means our forecasting result is positive, but the real result is negative. So we make a false positive forecasting. And similarly, we have TN, the true negative. So we make a correct negative forecasting, and FN false negative. So it means our forecasting result is negative while the true result is positive. So we make a false negative forecasting. So we use these four terms to construct the following evaluation metrics.
Yeah, but okay. Are they the prices or are they the volume?
Sorry, can you say again?
Are they, so let's say TP, and you say this is true positive or you forecasted positive, but what is that? Is that the price or volume or trade volume? It's the price, okay. Right?
No, it means so. So we have made, for example, we made a forecasting for today, for tomorrow, for the day after tomorrow, right? So if today actually the price move up, so let's say it's upward, the real result is upward, and our prediction is also upward. So we take 1 in TP. So we have the number, we have the amount of TP. I mean,
so it's the price. Is the you are focusing on the price movement upward, the so-called positive or negative.
Yeah. So actually, the precision recall all these things. So they are defined by the number of TP or number of FP, number of FN, and number of TN. So
what do we mean by number? Is day? How many times? How many? Forecast, the number of forecasts you mean?
Yeah. The number of true positive forecasts, number of false positive forecasts, something like that.
Okay.
So if we look at the third one, accuracy, so number of TP, number of TN, number of FP, number of FN. So the sum should be the total number of forecastings. And the numerator here, the TP and TN, so means it's the correctly positive forecasting and correctly negative forecasting. So, I mean, the number of these correctness. So you can take the accuracy as if we can only choose one metric from these metrics, so the accuracy will be the most important one. So it is the measurement of the correctness. Yeah, but actually we in our community, we need to consider all of these because sometimes we may more focus on the positive forecasting. So if we are going to do some investment, so the positive forecasting will be more important than the forecasting of the other side. So sometimes we should consider like precision recall, something like that. So to make it a standard the classification problem, so we just take all of these evaluation metrics into the consideration of our experiments. So here is the result for the synthetic named output data, and these the numbers before the parentheses on each column. So they are the evaluation metrics come from the benchmark model. So if we only use LSTM, so it means for the full synthetic data, so the precisions of performing LSTM only is around 74%. So it's a very good result from my perspective. And if we add the time to vector representation model, and so the numbers between the parentheses is additional. The moment if we integrating the time representation model into the LSTM model. So we will see here, if we also consider the time to vector representation model, so the result will be increased a lot, especially, in most cases, because we can see some decreasement like this example or this example. But on average, so we can observe a significant increment in all of these metrics if we add the time to vector representation model into the benchmark LSTM.
Yeah. And Buhong, in terms of those evaluation criteria, the so-called evaluation matrix that you just showed us, and who defined them? Is your team who defined it, or you took this from somebody else?
You mean this four metrics?
Yeah. So the criteria based on which you are evaluating your performance, the model performance. So who designed this? Who invented it? Is your team? You proposed?
No. Actually, so you can take it as a standard procedure of the classification evaluation.
Okay. Yeah.
So
okay.
We have to follow that. But as I said, it's in AI's community, so it might be different in finance community.
Okay.
Yeah, and another significant, another finding is that remember, so synthetic 1, synthetic 2, and synthetic 3. So the difference is that synthetic 1 has no seasonality. Synthetic 2 has weaker seasonality than the synthetic 3. So, and we can observe here, so the improvement of the time to vector model will give a larger increment to synthetic 3. So it just tells us, so if we can, when we observe a strong seasonality in the model from the data set, so adding the time to vector model or some like seasonality recognition model is necessary, and it will improve the performance very well.
Mm-hmm.
Yeah. So that verifying the first hypothesis. So if the seasonality representation model is necessary in this context. And when we move to the real data set, so for the capital named output data, so on average, we can observe a significant improvement in most cryptocurrencies. The only outlier, I would say not outlier, but the only exception is this digital currency, PEP. Okay, so we are trying to figure out why the model will have good result in some most popular digital currency like BTC, ETH, and SOAS. So these three are very popular, and they all have a large market size in reality. While PEP is something is some market with smaller market size, and we can find the difference of this model in the large market size cryptocurrency and the smaller market size currency. So that is some future work we are going to do. But our first or initial conclusion about the cryptocurrency is that performing the time to vector representation will also enhance the forecasting performance in digital currency. And if we replace the LSTM with attention, so you will see another, So you will see a bigger, a bigger improvement here. So, but I believe there's some typo here. We should have. I need to go back to check the statistics here, but because here, the sum is about 100%. Maybe I will send the correct version later. But our conclusion is also consistent. So if we just replace the attention, replace the LSTM by attention. First, attention is outperforming LSTM. And also, if we put the time to vector into to attention, so the combined model, and this model will have the best forecasting performance among the three proposed models. So that is what we do for the cryptocurrency. And finally, for the real equity market, so we also have the same result. So attention and time to vector will overall have the best forecasting result. Yeah. So that's what we do so far about performing these models to do the classification forecasting. And currently, our conclusion is that introducing the time to vector and introducing the attention mechanism will consistently improve the prediction, the classification prediction task. And what we do next, first, we are going to make a comparison between these machine learning models with advanced econometrics models to see if we can have, the machine learning models or the deep learning models will outperform the traditional statistical models. And our next future work is to extend our experiment to some more financial markets, not limited to the cryptocurrency, not limited to the selected Finland stock market, to see if our conclusion can be consistent across different markets. So that is what we plan to do in the near future. So I believe that's the end of my presentation. And thank you for listening, and any feedback and comments are welcome.
Okay, thank you very much, Buhong. And it's hard work for us, I have to say. And I now know how data scientists are working on financial market. So, but the first question that came to my mind is you mentioned in your future work. So I was thinking about, so in finance, there are some financial engineering, there are some mathematical finance, and probably to you, those are already conventional or traditional. So the first question that I have is, how do you, you said you are going to compare. So my question is, yes, because we now have machine learning, we are more advanced. What are the conflicts between the traditional or conventional mathematical finance or people who are working in this area and people like you? So you are applying the machine learning, AI related, and then to the similar financial question or question in finance. So what are the major conflicts do you see?
The major conflicts. Okay. I think I would not say the conflicts, I would say the different opinions or different attitudes. So towards the the financial market. So because as I said, so I used to learn mathematical finance. So so as a mathematician, I'm not a mathematician, but I know some mathematicians focus on the statistical property of this time series, of this financial data, and they are trying to model this using a beautiful mathematical model. So that is their focus. And for us, if we using the AI or machine learning approaches to do that. So as I said, so we have no or very few assumption or requirement about the data we are going to deal with. But that might be one benefit. So we don't need to do some preliminary work on that. But it will also cost another work. So many financial guys make the argument that so this machine learning model is a black box. So they don't know so why the result is generated. So any online meaning of this model. So actually we cannot explain as well because we have very few explanation power right now. So that is one. Yeah.
That's really good, actually, because I think we all need to think about this. So what are the differences? What are the advantages? And now we are using machine learning, and I want to know more because I want to know more about the advantage of using machine learning in finance in terms of the result. So the economic result, the implications, or policy implications, for example. So you use machine learning models to focus probably the similar thing that financial engineers who have already done. In terms of the result, do you think your result is better, or even though you do not have that much rich explanation, but do you think it is better because you do not restrict yourself with any distribution, any assumption, you just catch up everything that is over there, and then you get your result? So do you think in terms of the economic meaning, are you doing a better job?
Yeah, I would say I think so. Yeah, especially in this work. Also, we didn't show the result using the RIMA or GASH, but we already did that. Although we didn't show the result here, and the result shows that so the machine models generate a better forecasting compared with the RIMA and the GASH, this traditional statistical model. But as I said here, the future work. So we know there's some more advanced econometrics models. We have not tested that, but I cannot say our model will have a better result compared with the most relevant, the most recent or the most advanced econometric model. But one benefit, as I emphasized, so we don't need to we don't need to verify the data, the distribution, some statistical properties of that. We just feed the data to that. And another benefit is that so we have very well-developed algorithms, programmings, codes, so we can easily implement the machine learning models into the time series forecasting problem, and also when I describe the training of this work, as I said, so we need to spend like 1 week to finish the training and the test. But it's just because the limitation of the computational platform. So if we can have, for example, have like 8 or 10 GPUs, some hardware used in the in computer, so we can make it we can reduce the train time from around 1 week to maybe 1 day. So we can make it more sufficient. And also, we also observe some developments in other relevant field of computer science, for example, the quantum computing. And if we can rewrite the machine learning model in the quantum computing language, so it will reduce the computational time from maybe 1 day to just seconds because of the powerness of the quantum computing. So we can combine all these good benefits of the AI or computer science in different fields and to solve the financial questions. And that is the benefit, I believe, compared with the traditional mathematical way.
Well, that's really fascinating, and yeah, I know the technical part is really the key, but that requires the knowledge for that person who designs the program, and so that's one thing. The technical, but I will open the floor. But before that, I have another question that I have been thinking about. I was thinking about, so in finance now, so you worked in this paper, you work with the microstructure.
Yeah.
But those microstructure stuff is always assumed to follow the conventional finance assumption, let's say efficient market hypothesis and things like that. However, we do have another debate about, in finance, there is a behavioral finance.
Mm-hmm.
So people's psychology, people, sentiments, and this type of things. And the debate, it has been already going on for very long. Now, with the introduction of this AI, machine learning to finance, how do you think you can deal with the behavioral aspects of finance? Do you know, are there any examples that you can also apply machine learning, AI, to predict sentiments, behavioral things, psychological?
Yeah. So actually, one deep learning approach I explained in the presentation. So the reinforcement learning, which was adopted for the AlphaGo. Okay, so you can take it as one good example to implement, the AI into the behavioral finance. So one example of my current work or recent work is that if we try to model every component, every involved agent in the society, like individuals, like firms, like governments, something like that, as one agent in a complicated finance or economics network. So we can assign them some simple intelligence, some simple strategies, and they can interact with each other. Okay, so one possible research about this network is that, so if we are going to try to find, for example, an optimal, let's say the tax policy of the UK, so we just assign different tax strategy into the individuals, firms, some non-profit charity, something like that. So let them to interact with each other, and we will see the outcomes of the society. So by adjusting the intelligence or the strategies of involved agent, so we can see the different outcomes. As a result, we can select or we can search for the optimal tax policy for each involved agent. So that is one possible way to implement the AI into the behavioral finance. And we can also do the research from the opposite angle. So if we try to match the simulated society to the real world, to show, to make the simulated society show some similar properties, similar features with the real world. So we can also adjust the assignment of the strategies to the involved agent. And by adjusting these things, we can find, so under which condition, so the simulated world will show the similar features with the real one. And maybe the assigned intelligence or the assigned strategy can be an approximation of the motivation or the rationale of the people in the real world. So I believe from these two angles, we can combine the research of AI into the behavior finance.
So I understand that. So when you design the taxation, different structure in taxation, or you design anything, but that design, so the differences between those two branches is that this design should be based on your observation of behavioral thing, right?
Yeah.
Okay. But where is the data? How do you we do have some data and sentiments and things, and now social media, you can observe that. So is this type of data that you use if you are applying machine learning to this behavioral thing?
Not actually. So what we do is that, so what the reinforcement learning do is to start from nothing or start from no data. So it requires the input of strategy or the intelligence only. So just like the AlphaGo. So initially the scientists feed their rules. That's the only thing they have at the very beginning, and then the AlphaGo will play Go games, for so many times, and it will learn the optimal strategy from the games it played. So initially, no specific good strategy is required. It only need to know the rules. That's all. That's everything.
Yeah. So outcomes are quantifiable. So but there are something that cannot be quantifiable. But let's think about more about that. So let me open the floor to colleagues. So yeah, I know probably many of us are out of this territory, and but I think we picked up a lot of new things from Buhong's presentation. Do we have any other questions? No questions? No comments? I think I found this fascinating because I think I'm updated today by from what I heard from your presentation, and I got first-hand vision about how you work in how you deal with the finance topics. So if there is no more question or comments, maybe we should close this session. Buhong, do you have half a minute to conclude on your side, please? So, example, do you? Yeah.
Sorry, go ahead.
Yeah, it's okay. Okay, so do you have anything to say, Buhong?
Yeah. So yeah, I would like to know, but maybe we can discuss, after the presentation. After the So I would like to know. So how do people in finance and economics feel to? So how do you recognize? So do you think the explanation of the model is vital in, for example, the problem, like the classification problem or something like that? So if we only provide a machine learning model, and do I need to provide relevant explanation about why this model works in this problem or something like that? Do you think it's important?
Yeah.
Especially if we would like our code to be accepted by the financial.
Yeah. Yeah. Do we have any comments on that from the audience, from colleagues? Yeah, I think it's all about the application side. It's all about how you bridge from AI, from machine learning, between machine learning and the finance, the issue that you are talking about. So, I think I actually asked a lot of questions, and that reflects my own concern. So sometimes I need more explanation just to understand in a common term, so that the rationale or the intuition behind those definitions and those, I do not think we need the details in terms of your models. So as you said, that all the models are established in AI in that area, and so I think it's more about the connection. It's more about the application side. So, but thanks, Buhong. So let's continue with the conversation when we meet, and we have some other opportunities. And I'm sure you are applying your data science to different issues, in finance, in economics. So I can see a lot of opportunities there. So I want to conclude this session. I want to say this is the last session of our academic year. And I want to thank everybody for your time, for your support, either your presentation or your time devoted to discussions of those seminars. So we do not have any scheduled seminars in term 3 for this year. We may have one-off activities depending on the preparation of other stuff, but we normally after finish the seminar we will organize 1 or 2 sessions, one-off, either a guest lecture or some other type. So I just want to wish everybody the best for the rest of the academic year, and then we see each other maybe at the beginning of next academic year. Okay, thank you very much.